All right, why don't we go ahead and get started. So welcome back, everybody, to EE290C. So obviously homework is due in an hour and 20 minutes. So I guess if you're turning it in here, it looks like the unofficial, collection point is right over there. So just, pass it down. I saw there was a few in my box, just outside my office. So that's fine too, of course. I guess any really, really last-minute questions on either that or lecture material or anything?
Yeah, what's the answer to number?
So last time we were talking about basically timing and sort of related issues with clocking. We talked a bit about kind of what are the different types of timing that we could run into. And then we basically finished almost all of that. There was just kind of the last part about clock distribution, which I wanted to just briefly mention. We'll actually have a lecture a little bit later on that'll go into a lot more detail on that. But basically maybe just a sort of a quick reminder for everybody. We talked about kind of having clock and data recovery systems and why that was somewhat advantageous from the standpoint of eliminating deterministic errors as well as allowing you to have different crystals on different boards. We then also talked a bit about sort of the implications of that in terms of how you have to have buffers in order to deal with the frequency offsets. And then we finally sort of just made a note about what's the difference between really a serial link and a parallel link. So again, the last thing I just wanted to sort of briefly mention there was that I've mostly been talking about sort of, let's say, system issues in terms of just how clocking works, period. But there's actually a lot of, let's say, just physical issues in terms of getting really the clocks that you want, and in particular, getting them to have very low jitter. Because you can imagine if you've got some, let's say, big chip, I don't know, let's say, as an example, a microprocessor or something like that. You've got all the links kind of distributed on one side over there. Well, this side over here could easily be order 10 to even about, 15 or maybe even 20 millimeters on a side or so. Okay? So if you think about that, I probably don't want to have like 10 different crystal references out on the board for all of my links. So that means that, okay, there's probably just one little crystal coming in somewhere off on the chip, maybe on the bottom side of the chip. So of course that means that either you have to sort of take that reference clock and distribute it out over, to all of these different links, and then locally have them generate the higher frequency clocks in some way. So as an example, the PLL or something like that. Or maybe you would even, and I'll just draw it on the other side of the chip over here, maybe what you do is have just, one PLL over here in the center and then distribute that higher frequency clock out to all of these different links. Okay, now you can imagine that with both of these, you have to be really, really careful with how you distribute those clocks. Because you can imagine to cover about 10, 15 millimeters or so, you're going to pick up a lot of loss, even at the lower frequency of the crystal. And so that means that you probably have to insert some buffers. Well, guess what? Those buffers usually are sensitive to the power supply, and so you'll very easily pick up quite a bit of jitter just from distributing that darn clock across that distance. Okay? There's also, of course, another trade-off, which is just how much power does it take you to actually distribute that clock. And from that standpoint, doing something at the lower frequency seems more attractive just because there's lower loss there, there's lower sort of CV squared F paid just because you have a lower frequency. But of course that means that locally, and I'll just draw it over here on the side, that means that locally each one of those tap points would have to multiply that clock frequency up to actually get to that very high frequency you need on the actual line rate itself. So you kind of have this trade-off between just having one PLL and then amortizing the overhead of that PLL across the entire link versus distributing the very high frequency clock across that entire distance and then paying all of the clock power associated with that. And of course, again, actually all of the clock jitter and actually basically noise that you'd be picking up on the clock, which could cause just functionality or performance issues. Okay, so as I said, I just wanted to sort of briefly mention this here because this is actually a pretty big issue, and we'll probably talk about it a little bit more probably in 3, 4, maybe even 5 weeks or so. But just kind of give you guys a heads up that clocking is not just about sort of how you figure out locally what's the right point to sample. A lot of that is also about just distributing the clocks to all the different links that you need to be working with, because when you have to cover large distances and have these pretty high frequencies, and of course still maintain very low jitter, turns out to be a pretty big issue. Okay? Any questions on this? Or? Okay, great. Like I said, we'll spend a lot more time on that a little bit later on, but I just kind of wanted to briefly mention that here because, again, it's a pretty big issue that you will definitely be dealing with at some point in your career. Okay, so with that, let's actually go ahead and move on to the next set of slides that I just handed out today. And so really the next sort of set of topics that I wanted to talk about is actually doing some of these equalization techniques. So hopefully most of you guys are familiar with what I mean by equalization because you saw it back in 240, but if not, I'll kind of briefly remind you. The only other thing that I'll mention is just that this lecture in particular will have a little bit more math than I usually do. It'll even have some matrices and things like that, but don't worry, nothing too sophisticated, like, you should be able to get it, and if not, don't worry, you'll have a homework that'll make sure you got it. Okay, so as you guys hopefully sort of remember, we looked at a few of just what those channels, the link channels, actually looked like from the standpoint of going through that whole backplane with all the connectors and things like that. And when I say channel, of course, I mean something like the S21, or just in the frequency domain, the magnitude of what you see at the receiver versus what you see at the transmitter. And I'm just sort of repeating a plot of what a few of those channels actually look like here, just to kind of, again, give you an idea. Okay? Now, the point here really is that if you just sort of take a glance at these, there's kind of a couple of things that should be immediately obvious. So first is, all of these are kind of low pass, right, or band limited, so to speak. Meaning it doesn't look like you can go out to just any arbitrary old frequency because the loss actually starts picking up pretty quickly. The other is, and we'll talk about this a little bit more later, for some of the channels you see these really deep notches and ripples and things like that. Okay, so those in particular, there's certain frequencies that just don't look good, right? Okay, so the point here really, of course, is that why do you care about this? Well, why you care is that if you have a band-limited channel, meaning you have a low pass or sometimes known as a dispersive channel, and that basically means that even if you take some very nice, clean, short transmitted pulse, that you had over at your transmitter that you built, and then you sent it down the channel, by the time you receive it on the channel, which is what this kind of green trace is showing you, it's going to be sort of spread out, right? And in particular, the way to see that, all of these like black dots here, those are sort of like what would be the voltage you'd get at the clock-spaced samples, or at the bit-spaced samples, okay? So what you can see is that even though you may be sent, from a bit standpoint, 0, 1, 0, by the time it arrives at the receiver, you have sort of, okay, 0 here, but some stuff over here, actually a pretty attenuated signal here, still some residual stuff here, and so on and so forth, okay? So the stuff that's really associated with just sort of the channel being low pass like that, or again with kind of the dispersion, that's kind of the stuff that's sort of just spreading the pulse out locally, okay? But as we talked about a lot, you're also going to get reflections, right? So there's just going to be points along that propagation path where the impedance isn't quite right, or you went through a connector or something like that. And what that'll usually show up as is these little sort of ripply things down here at some later time. Right? Those are basically reflections that took additional time to propagate down in the channel and then finally show up at the receiver. Okay, so fairly common type of link response here would be something where there's this dispersive sort of close-in kind of response. And then sometime later, there's these reflections that just kind of come in and cause a little bit of additional ripple or weird-looking behavior there. Okay? So hopefully, again, many of you guys remember this from 240, but why does all this matter? Well, the point is that, of course, if I take my nice, clean transmitted pulses at the transmitter over here, and then I pass them through a channel that looks like that, well, by the time they get to the receiver, very easily that distortion could make it so that you just actually don't receive the bits that you want to receive. Okay? So here I'm just sort of showing a simple example where I had a long string of zeros, and then all of a sudden I do a 1, a 0, a 1, and then another 0. Okay? So what you can see is that actually this green trace right here, that's kind of like the first sample associated with this first 1 right here. What you can see is that because I have so much loss in this channel, that first sample doesn't even actually get up to sort of my receiver's threshold. Right? If you kind of think about it, my receiver's threshold would have to be at about a half here. So that first sample, because the loss is so large, doesn't even actually make it all the way up there. Okay? So another way of saying that is that the so-called inter-symbol interference, or ISI, basically all of the ISI from the previous 0 bits has kind of added up and stopped this first sample from actually getting all the way above the threshold. Okay? The other thing you should notice is basically if you sort of look at this red is kind of the composite waveform, but in particular if you look at this sample point right here, notice that there's a very, very small difference between what you actually got right here on that first sample and what you get on this second sample. Even though, remember, what you transmitted was a 1, 0, 1, right? Doesn't look like very much of a 0 right here. It's kind of like totally shifted off, right? Well, it turns out that happened because basically this green pulse over here, something like 0.2 of the amplitude that you sent from that green pulse is still sticking around in the channel. Okay, and not only that, actually, there's 0.1 of amplitude from the pulse that will be coming, okay, from that blue one, which is also kind of pushing this guy up over here. Okay? So basically, anytime you have this dispersion like this, what it means to spread those pulses out is that if you try and do things that are changing very quickly, then that tends to mean that you don't actually get the changes you want. Okay? You actually see things that are kind of smeared out and look very flat, even though you were trying to change them quickly. Okay? So of course, again, the point is that you care about this because you can see in this particular example, I've actually made the ISI so bad that I will completely not receive the bits at all. Right? All three of these would be decoded as 0, even though they're supposed to be 1s. Yeah?
I'm just wondering, can you actually do those communication people have been doing for this ISI problem? Like OFDM, you actually just switch to the frequency domain. Can you actually do that?
Okay, great question. So the question was, can you switch to something like OFDM, which stands for orthogonal frequency division multiplexing? Okay, so we're going to talk about actually a lot of communication stuff that people are indeed doing on links. Turns out if you look at most chip-to-chip IOs, they are not using anything like OFDM. Okay? So if you looked at, actually it's not exactly Ethernet, but if you looked at like ADSL and things like that, those are actually using something very similar, but they call it multitone or discrete multitone instead of OFDM. But the main issue or the main reason that these things aren't used is basically I don't know of any way of actually building that doesn't cost you at least an order of magnitude, if not even 2, more power than what you can do with the techniques people use now. That's really the main issue. There was actually some research that was done on that, maybe 3-4 years ago. It's still kind of, let's say, an interesting area to think about. But turns out it's pretty tough to actually justify the sort of complexity benefit in comparison to what people are doing now. So we'll talk about that some more, but that's a great question. Other questions on this? Or? Okay, so point here only again being you care about, what the channel is actually doing to you, because of course, if you had something like this, and you can look at this in the eye diagram as well, you can kind of see if I took my pulses and I passed them through this channel, my eyes are completely closed, right? I can't tell what the heck is a 1 and what the heck is a 0. I have no margin. I'm just going to get errors all over the place. Okay? So what are you going to do? Well, of course, you're going to apply sort of the simplest thing you can think of, which is if you have something that's sort of doing something bad to you, do the reverse of the bad thing, and then hopefully on the net get something that looks okay, right? So that general process is just what's known as equalization. And it's called equalization simply because it's just trying to make it so that all of the frequency components all have the same response. And if you think about that, if they all have the same response, that means it's a wide bandwidth thing. It means you're not distorting in time the thing that you sent. Okay? So in general, if you have something that's, let's say a low pass channel, if you take that through something that looks like a high pass, quote unquote, equalizer, then at the end, you'll get something that hopefully looks quote-unquote flat. Okay? So that's really kind of the name of the game with equalization. It's just trying to take those pulses that got messed up because of the frequency response of our channel and bring them back to being nice, clean pulses. Okay? Yeah?
How about the phase?
Okay. So technically speaking, you actually have to correct the phase as well. I didn't really show it here, but indeed, if you have some phase distortion that's causing different components to smear out the pulse, indeed, you'd probably want to, or you need to correct that as well. So the simplest way to sort of think of it is, even though I keep drawing in the frequency domain, and we'll talk about this a little bit more later, what you're really trying to do is, if I used to have this, nice sharp pulse at the transmitter, then what I want to do is, by the time I go through my channel and my equalizer, I want to get that nice sharp pulse back. That's really the goal of equalization. So whatever you have to do in the middle to get that back, that's what an equalizer is supposed to do. Yeah?
So I have a question. So in all this, you have assumed that the channel is linear.
Okay.
So how do you justify it?
Okay, well, so the good news is, if you remember I said way back when that usually the backplane is passive. So unless I'm doing something really, really nasty, most of the time it is indeed justified to treat it as just being a linear channel. Because unless I have, voltages so large that I'm melting metals or, melting dielectrics or something like that, it basically does look very much like a passive linear channel. There's maybe some caveats to that with, if you look at like the ESD, the capacitance of the ESD, maybe it gets modulated. But again, as long as your signals are kind of reasonable, that doesn't have too big of an effect on kind of what I'm saying here. If it is nonlinear, of course, you could deal with it. But generally speaking, I haven't run into any links where I really had to worry about that yet. It's a good question. Actually, I'll take that back slightly. Usually if it's nonlinear, it's the circuits you built that are causing it to be nonlinear and not, not the channel itself that's nonlinear. And we'll maybe talk about that a little bit later. There are some reasons why maybe you would intentionally make it nonlinear. In fact, we'll talk about that even a little bit today. But for all intents and purposes, just think of it as being linear for now. It's a good question. Other questions on this? Or? Okay, so just to sort of maybe set the stage a little bit, equalization is by no means a new topic. Okay, this has been around for a very, very long time. If you sort of notice, there's this patent here from about 1941, which was actually filed in about 1939, which was invented by a guy, some of you guys may have heard of, Bodie, right? So this was actually for telephone systems, right? Because basically you had these long cables people were stringing trying to get across the United States, and of course, cable has loss, just like we talked about. So even way back then, they sort of said, well, okay, I still want to hear everybody's voice. So they actually built these little equalization systems just to try and make sure that that cable would effectively allow you to transfer over these very long distances. Okay? So again, equalization as a topic in general, definitely not new. Okay? Definitely not something that's been invented just for high-speed links. But there are actually some fairly unique challenges when you actually look at these high-speed electrical interfaces. And really the challenges that kind of drive everything from the equalization standpoint is first of all that, again, we're talking about very, very high performance. So we're talking 10, 20, maybe even 30 gigabit per second kinds of throughputs. Okay, so much, much higher than just about any of the other communication systems out there that you deal with. Except for maybe optical, which again, I'd count as being under this same boat. Okay? The other thing is that, again, not only do you have to achieve that very high throughput, but you have to do it in very, very tight power and area constraints. Okay? So again, this is saying something like, okay, I want that 20 gigabits per second, but I want it in, like the size of a couple of pads and, in like 10 or 20 milliwatts, right? So that very, very tightly constrains what are the techniques that you can really apply, or really it forces you to be kind of creative in terms of how you build things, because you can't just sort of attack it brute force and meet the constraints that you're interested in. Okay? So for today's lecture, I'm mostly going to focus on sort of just, let's say, not exactly theoretically, but what kind of drives the types of equalizers you might be interested in. And then probably in about a week or so, we'll actually start diving into a lot of detail of how do you actually build equalizers and what are the trade-offs and sort of what are the power issues and things like that. Okay? Okay, so again, just to sort of maybe to set the stage a little bit, as maybe you've noticed already, just like in wireless and just like in many other fields, there's lots of different acronyms that are out there for equalizers. Okay, so links we talked about a lot of acronyms for clocking and for types of links. Well, okay, same thing with the equalizers. Okay, so you'll probably hear things like CTLE or ZFE or DFE or FIR or MMSE. Okay, so I'll explain kind of what all these different things are, or at least I'll try and give you at least a hint for most of them. But the kind of main thing to keep in mind with all of these equalizers is essentially just three basic distinctions. Okay? The first is essentially whether or not that equalizer is linear or nonlinear. Okay, and we'll actually see sort of an example of both of those in a second and why you'd even want to deal with something ugly and nonlinear. Okay? The second is essentially just whether you deal with things in continuous time or discrete time. Okay? Nothing too complicated, but again, we'll see sort of what the trade-offs there are in 1 second. The final one, which maybe you've heard of a little bit before, but will turn out to actually interact with this first thing, is just whether or not your equalizer is built purely to minimize the inter-symbol interference, or the ISI, versus you actually try and minimize some combination of the inter-symbol interference and the noise. Okay? And again, we'll see sort of what the issues are there in a couple of slides. Okay? So let's just start out. And I'm going to start out with what I think is the quote-unquote simplest equalizer. This isn't actually historically what people applied first. Or rather, I should say, at least in links, it wasn't what people applied first. But from your guys' standpoint, I think this should be the easiest because this is the one that hopefully most of you guys remember from 240. Okay? So the simplest equalizer from our standpoint is what's called a continuous time linear equalizer. Or again, a lot of people like to call that a CTLE for short. Okay? So the idea here is pretty simple, right? So basically, if my channel was somehow simple, and what I mean by that is something very specific. In other words, just as an example, let's say it was a first order low pass filter. Okay? Well, if I have some first order low pass filter as my channel, then what I can basically do is just build some analog circuit that essentially just approximates the inverse of that low pass filter. Right? So in other words, to be very specific, all I'm saying is that if my channel looks something like this, where let's say there's some omega naught here that, things start rolling off, and that's the magnitude of my channel, right? If I basically take my signal and I pass it through that channel, and then I pass it through something that looks like the inverse of that channel, so this is now going to be my equalizer response. Of course, and that's going to look something like this, where again, this is that omega naught. Right, then if I've done things well, then out at the output over there, I should get whatever I transmitted. Right, so let's just call this VTX, this will be VRX. So again, if I do that equalizer right, then VRX should really be just the same as VTX, right? Nothing magic there. Like I'm literally just saying, whatever the error was, whatever the filter was, I'm just going to build the inverse of that filter, and as long as everything is linear, H times H inverse is 1, right? Okay, so I'll sort of, remind you guys how we actually build this in 1 second, but any thoughts on whether, what I wrote here, even for this very simple example, works exactly the way I said it does, or are there maybe some issues we have to worry about? Yeah?
There's phase distortion.
Okay, well that's fair. So, but I guess my intent was really to take, H inverse like in the S domain. So whatever the S transfer function was for the first one, I'm literally going to try and do the inverse of that for the second one. So that would take care of the phase distortion too.
I mean, you can't have that going up with frequency.
Okay, so why not? Why can't I just have this, keep going up like this? What's the problem?
Can generate power.
Say that again?
You can generate power.
Oh, okay. Well, you said you could generate power. I guess so, yes. I mean, the point is, of course, any real circuit that I build won't have infinite bandwidth, right? I'm always going to have some finite bandwidth unless I'm either generating power or somehow, magically burning infinite power or something like that, right? So what you're basically saying is that, look, any real circuit has finite bandwidth. And so what that means, and I'll just draw it, of course, in a different color, is that, instead of really getting that, you're going to get something that looks like this, right? So, by the way, if I get something that looks like that, what's kind of like my overall channel response? What does it look like from the transmitter to the receiver? Not a trick question, by the way.
Then it should be all pass something.
Well, I'm saying if I include this blue behavior here, the fact that I actually have some finite bandwidth.
Low pass with a notch, with a blue.
Well, if I do things right, then it'll basically just be low pass. Right? It'll be low pass pretty much up to whatever that frequency is right there. All right, because if I got things perfectly correct up in this region right here, and I exactly compensated for the error right there, then it'll basically perfectly match right up until I get to this point, and then it'll just start dropping off, right? Okay, so roughly speaking, where do you think, since you're building the circuit, where do you think you want to put this, roughly speaking?
5 times the clock.
Say that again?
5 times the clock.
Oh, okay, so you said 5 times the clock. Remember, I'm working at about 20 gigabits per second. So that's, depending upon how you count it, somewhere between 50 and 100 gigahertz. Which if you can do that, in low power, great, we should talk.
Should be half the bitrate.
Yeah, okay, so somewhere between half to about 2/3 of the bit rate is where you typically put it. But basically, it's directly related to the bit rate. And it's usually on the order of, as you said, half to maybe 2/3 of the bit rate. Okay, and that's, if you're interested in where that number exactly comes from, you should come talk. But ballpark, that's where it is usually. Okay. Okay, so that's actually, from the high-level standpoint, really all that's sort of important in terms of continuous time linear equalizers. I'll just mention sort of briefly, or maybe remind you guys briefly how you actually build them. Again, I'm hoping that most of you guys looked at this quite a bit in 240. So if you don't remember, then you can always go back and sort of take a look at the videos there. But basically, typically you'll build this on the receiver. And the reason for that is just that the impedances you're dealing with are higher at the receiver. So to get a certain voltage gain or a certain signal swing, usually it takes you less power to do that versus at the transmitter. And again, this, just sort of as a reminder, there's lots and lots of different ways you can do it. But one of the most common ones just looks something like the following. So what you basically do is just degenerate some differential pair. Let's call that VI plus, VI minus, VO minus, VO plus. Right, so the idea here being, of course, that at low frequencies, the gain is degenerated by that resistor. So you have less gain than you might have otherwise had. Whereas at high frequencies, this capacitor basically kicks in and shorts the two sources together, which gives you higher gain at higher frequencies. Which, if you remember, we were trying to build a high-pass filter, or maybe you can call it even a band-pass filter. That's exactly what we were interested in here. Okay? So again, lots and lots of different ways you can build these equalizers, but this is kind of the most common one, or hopefully one that you've seen a couple times before in 240. Okay? So this indeed actually works reasonably well, but there's a few, let's say, issues that you get into when you really start looking at, let's say, realistic channels. So what do you guys think are some of the issues you might face in terms of doing this with realistic link channels? Any thoughts? Yeah.
The pole location, 0 location's fixed.
Ah, okay. So you said the 0 location is fixed, which would mean that if I'm working on a bunch of different channels, I kind of have a problem because I can't really tune it. But actually that one, okay, maybe it's a little bit annoying, but it can probably be fixed by sort of tuning the components inside of there. There's another question about how you tune it. We'll maybe talk about that a little bit later, but that you can potentially fix. There's actually a couple more issues. What else do you guys think? Yeah.
You can only get a 20 dB per decade increase. I mean, if it's like more than that.
Okay, well, so you said you can only get 20 dB per decade. The issue I'm getting at is actually closely related to that. But what if I said, no, fine, really, I want you to do more than 20 dB per decade? What do you have to do? How do you get more than 20 dB per decade sort of slope out of the
Add one more. One more zero.
Okay, you said you could add another one,
Yeah.
right? So indeed, you could, and just because I'm lazy, I'm not going to redraw the whole thing. I'll put a box around this. Indeed, you could take that and build another one like this. That's certainly true. Is that okay, or can we keep doing this, or what?
Well, it just basically kills gain at low frequencies, so you add a bunch of noise.
Ah, okay. So you said something about noise. That is actually definitely very true. We're going to talk a lot more about that later. All right, so you said if I keep having to do boosts like this, then noise is definitely going to be an issue, and that's certainly true. We'll talk a lot more about that. Anything else in terms of just, let's say, how many of these stages do you think you can cascade, or what's maybe the annoyance with that?
Power.
Okay, yeah, there's certainly some power issues. We're not going to talk too much about the implementation, but that's certainly an issue. Let me maybe give you guys a hint. And actually, you know what? I won't even draw it. I'll just go back to these pictures right here. What does this channel look like? Does it look like a first order low pass? Or actually, well, okay, there's actually 4 channels there, but do all 4 of them look like first order low pass? They don't, right? This is an example, even with the one that kind of looks low pass, there's all these like weird Ripley junk on it, right? So if you wanted to build an analog circuit that was the inverse of that, how many poles and zeros would you need?
Lots.
Yeah, a lot. I don't know, but a lot, right? Even worse than that, if you had some deep notch like this, right? Now you have to really build some very funky analog circuit, which, by the way, the Q of that notch might even be higher than the Q of, what you can get with your on-chip components. Okay? So, it's, basically what the kind of the meta point there is that these linear equalizers are very nice as long as you have sort of a simple channel response. But if the channel response starts getting more complicated, again, just as an example, let's say it looks something like that, starts getting a lot trickier to actually implement that equalizer. Okay, so indeed, you could just start cascading a bunch of stages and playing with poles and zeros and doing feedbacks and all kinds of stuff like that, but at some point it just gets painful. Okay? So that kind of brings me to the next, let's say, type of equalizer, which is basically just a linear finite impulse response filter. Okay, so what I've done now is I'm going to be switching from the continuous time domain to the sampled domain. Okay, so I'm just going to first draw what an FIR filter looks like just to remind everybody. And then I'll maybe sort of see if you guys can figure out why an FIR filter might actually have some advantages relative to the continuous time linear equalizer, given the specific issues that we mentioned a second ago. Okay? So with an FIR filter, and again, I'm hoping this is kind of a review for everybody, but just in case, I'll quickly draw it. What you're basically doing is, again, you're working in the discrete time domain. And what you're going to do is you're just going to take delayed samples of the data, weight them by different coefficients, and then add each one of those samples together. Okay, so something that looks kind of like this. And of course, you can keep on extending this to more coefficients like that. Okay, so just from a terminology standpoint, since I'll probably say it and may forget to define it later, each one of these sort of coefficients is usually referred to as a tap. Okay, because it's kind of like a tap off of this delay line. Okay, so this would be, for example, a 3-tap FIR filter. Okay? So now, and I'll talk a little bit more, sort of where or how you'd implement this in 1 second. But let's assume that you can implement this one way or another. What's potentially advantageous about doing the equalizer this way versus trying to build it out of a sort of circuit that looks something like this? Any thoughts?
You have more flexibility and you can easily make it adaptive channel or.
Yeah, that's basically it. It's basically more flexible in the sense that, right, each one of those taps has an independent coefficient, right? So that just means that it's slightly more flexible, or it's perhaps even a lot more flexible depending upon how many taps you have, of course, in terms of trying to create these weird-looking shapes. Okay? Because basically by sort of futzing with a combination of these 3 taps, you can create some shape that looks very strange versus what you could do with kind of a straightforward, like continuous time filter like we had in the previous example. Okay, that's really actually kind of the biggest differentiation there. Okay? The other sort of thing to point out there is that this is usually done at the transmitter. Okay? Anybody know why it is that you usually do this at the transmitter, and not you? Yeah.
Also, you don't need like an ADC. It's probably easier to.
Okay, so you said no ADC. That is true, although that's probably not, let's say, the fundamental reason. I mean, that is true, but.
You can easily delay it by using flops.
Ah, there we go. It's actually the delay that's the biggest trick. Okay? So it just turns out digital delay is a lot easier than analog. Okay, and in particular, digital delay, or rather, if you build delays with digital gates, you can do that without noise. If you do it with analog, it's kind of a pain in the ass. Okay? So, Igor is right. It does actually save you an ADC. Although, by the way, you could actually build this on the receiver with an analog circuit too. It's just, if you do it with an analog circuit, then you can't actually use the digital delay. Okay? And then you do need an ADC, and there's some other issues with that. Again, we'll talk some more about the real circuit stuff. For this lecture, I mostly want to focus on kind of the high level, what are the trade-offs there. But for this, it really is that digital delays are nicer than analog delays, which is why you tend to put this at the transmitter. Okay? So if you kind of look at what this sort of ends up looking like, if I really was to build this sort of FIR filter on the transmitter, the way you typically will do it looks something kind of like this. And again, we'll talk a lot about this more later on. What you kind of do is you take whatever your transmitter used to be, and you kind of split it up into little smaller chunks. Okay? And then what you do is you feed the inputs to your transmitter of each of those chunks from essentially delayed versions of the digital data. Okay, so an example, each of these boxes is just meant to be a flip-flop. So this is kind of like just the shift register, right? So as an example, if this is like my, let's say, my main data that I'm sending, then all of the stuff after here, those would all be like delayed things that in terms of the taps. Okay, so these things would be sort of trying to equalize the response of the channel. So again, just from a sort of terminology standpoint, all of the stuff that's kind of down here, meaning it's after that big guy, is what's called a post-cursor tap. Okay? So cursor just means like what's your main largest amplitude. That's kind of like the actual bit that you're trying to send. Everything that's actually, everything that's essentially before that, for example, that guy, is called a precursor. Okay, so pre and post is just referring to relative to what's the biggest amplitude that you have. Okay? So just to kind of give you an example of how something like this would work, let's say that this red trace here was what you had from the original channel response. and you wanted to equalize that, well, it turns out for this particular response, what you might do is have something like this black pulse that's being transmitted here. Okay, and notice this black pulse would be kind of a pain in the butt to build in an analog circuit. I mean, it could be done, but you know, doing it exactly to control these levels and things like that would be kind of annoying. Okay? So what you can see is this particular thing has one precursor, and that's helping to kind of kill that initial slow rise, right? Then it has this main tap, and then it has a big postcursor whose job is just to really bring that whole thing down so that you don't have a lot of residual energy left afterwards. Okay? So again, what you can see is if you've done this right, then you can now see sort of a nice, clean bit being received at the receiver. Okay? Make sense to everybody? Or? Okay, so now's where we come into sort of one of the other, let's say, question about what type of equalizer this is. And in particular, to get there, it's sort of useful to walk through just how would you actually set the coefficients for some equalizer like this? Because as I said, you know, the whole reason we went to this FIR is it is a lot more flexible. But unfortunately, it being a lot more flexible also means it's a lot more of a pain in the butt to figure out what the right sort of thing to do there actually is. Okay? So, you know, just as a warning, this is where I'm going to be starting to do some math in a second. So, you know, just pay attention. You'll be doing some writing of math. But again, I promise it won't be too bad. Okay? So if I want to figure out how to set those coefficients, let's just first assume that I know what the channel actually is doing to me. Okay? We'll talk, again, maybe in a couple of weeks or so about how you'd really figure out what the channel is, how you'd estimate the channel. But for now, let's assume we know what it is. So the most basic approach to sort of setting these equalizer coefficients is to do what's called zero forcing. Okay? This is also referred to as a ZFE, so zero forcing equalizer. So the basic idea is very simple. Let's say I had some channel response that I started out with. What a ZFE is going to try and do is just force it to look like a perfect single bit. Okay? So in other words, it's going to try and zero out all of the ISI. Okay? So again, keep that in mind because I'm going to be starting to do some sort of derivations in a second. But if you keep in mind that that's kind of our goal, then hopefully the math won't be actually too bad. Okay? So let's see sort of, you know, if we can come up with a simple formulation that tells us how is it that we should be setting the coefficients in that equalizer. Okay? So to do that, I just want to sort of draw a quick block diagram to remind everybody what it is that we're talking about here. Okay, so what we're basically doing is we have some transmitted data bits that I'm going to call just XTX. Okay? What we're then doing is we're passing them through that FIR filter, which is our equalizer. Okay, and I'm going to call that WZFE. Okay, and just as a reminder, that's a discrete time equalizer. Okay? Well, coming out of that is going to be some analog but still discrete time quantity, some voltage waveform, which I'm just going to call YTX. Okay? Then that is going to pass through my channel. Okay, now in this particular case, because we're working with discrete time, I'm actually going to sample the channel at the same rate as I sampled my data. Okay, so instead of it being like a continuous time channel now, I'm just going to sample it in the time domain, or rather in the Z domain, to get discrete sample responses. And I'll sort of show you how that works in 1 second. Okay? So of course, coming out of that, I'm just going to call this ZRX. So this is like the analog received voltage. Okay? Is this everybody with me so far? Okay, so first things first, in terms of the channel, the thing to remember is, you know, when we drew these block diagrams kind of with linear systems and things like that, whenever we have these arrows kind of going through this way, what we're really implying is that whatever this response is being convolved with whatever's going into it, right? So in other words, if I want to know what ZRX actually is, then what I have to do is I have to take the time domain responses in the channel, which I'm just going to call H channel with a lowercase. And again, I'll sort of show you how I'm going to deal with this in 1 second. And I'm going to be convolving those with whatever my transmitted waveform was. Okay? Okay, well now, so just as another reminder, that transmitted waveform, that's really just formed by my equalizer, right? and that equalizer would have some, some number of taps in it. Let's say n taps. Okay? So let's just do an example. Let's say that I have a 3-tap equalizer. Okay? So what I'm going to do now is I'm going to switch to writing things in sort of vector notation, because as you'll see in a second, it's really convenient to use vector and matrix notation to then figure out what are the sort of optimal settings that I should be using. Okay? So for that 3-tap equalizer, let me call this WZFE. I'm just going to say that that's just some vector with 3 entries, with, let's say, W0, W1, and W2. Okay? So each one of those is just the coefficients that I drew, over here in that original picture. Right? So W0 is just the coefficient of the thing that comes straight out. W1 is with 1 delay. W2 is with 2 delays. Okay? So the other thing I should mention here is that I'm basically assuming that, remember, since my whole goal is just to make it so that if I took 1 bit over here, I get 1 bit over there, I'm sort of intrinsically assuming that the data that I'm sending is just 1 bit. Okay? Because since it's a linear system, if I make 1 bit transfer correctly to 1 bit at the end, then everything will work out fine. Right? Okay. So now what I'm going to do, and again, this is just really to sort of help the formulation. What I'm going to do is, instead of sort of dealing with vectors and writing these convolutions and things like that, I'm going to write the channel as what's called a convolution matrix. Oops. Okay, so fancy word, but doesn't, it's actually not that complicated. All this really means is the following. So if I looked at my channel response in the sampled time domain, right, what you can imagine is that I'm going to have something that looks sort of like this. Right, so I'm going to have some, let's say, initial magnitude at the first sample, some other magnitude at the second sample, some other magnitude at the third sample, and so on and so forth. Okay? So for this particular example, I'm just going to assume that everything after those 3 is 0. Okay, just because I want to use a small example to make my life easy. Okay? So what I'm going to do is I'm going to use this to form a matrix that would tell me if I took this transmitted vector and passed it through the channel, what would the output look like versus time? Okay, so kind of the way to think of this is that this dimension here is kind of implicitly representing sample time. Okay? So I'm just going to call this capital H channel. And just to give you an idea of sort of what that looks like in this specific example. So what I'm basically doing is I'm just going to take the channel response. But since I'm doing this convolution, I have to sort of shift it by 1 position each time. Okay? So as an example, for the next bit position, I have to do that. Okay, then for the next one, I have to do that. Okay, and then if, of course, I just fill in the zeros in the places that are left, then I end up with something that looks like this. Okay? So, just in case you're maybe sort of confused, the reason why this ended up as being 5 by 3 is just that this 3 over here, that's just how long my equalizer is. And the 5 is just related to, I have 3 sort of responses or 3 taps that I'm keeping in the channel. And these extra 2 are because I have to convolve it with something that has a length of 3. Okay? So in other words, this sort of dimension here is always the number of taps in my channel plus the number of taps in my equalizer minus 1. Okay? And again, trying this on an example makes things usually much more clear than just hearing me say it. Okay? So everybody comfortable with this, or? So the sampling rate here is my bit rate. So in other words, if I'm signaling at 10 gigabits per second, I'm sampling at 10 gigasamples per second.
Okay.
Does that make sense, or?
Yeah. But is that enough to represent the channel well enough?
Ah, okay. So that's a great question. We're actually going to talk about that a little bit more later. From the standpoint of the data, that's sufficient to get the Nyquist frequency of the data. Okay, because the data, if I have 10 gigabits per second, the fastest the data could be doing is 5 gigahertz. Because it would be 10, 10, 10, right? So from the standpoint of the data, it is sufficient for Nyquist. But we'll see in 1 second, it's not quite sufficient for some other things that we may care about.
Yeah, so can you have a precursor for the channel?
Sure, absolutely. So I just didn't put it here, but you can indeed have a precursor. And I'll sort of point out in 1 second the implications of that in terms of the formulation. Okay? But you can indeed have a precursor. Everybody with me, or? Okay, great. So now that I have that formulation, now we can actually start talking about, how would you figure out what the right value is for the tap, or for the coefficients. Okay? So again, just as a reminder, I'm going to redraw the block diagram over here, just so that everybody remembers what we're dealing with. So we have our equalizer, which again I called WZFE. That's the transmitted pulses coming out of that. Then we have our channel response. And finally, the received analog voltage. Okay? So remember, the whole goal with building this equalizer was that we wanted that received analog voltage to kind of be a perfect bit. So what I mean by that in the sample domain is just something like the following. So if I was to look at my desired voltage at the receiver, of course versus just the sample number, where I transmitted a single bit at the transmitter, then I want at the receiver just something that looks like that. Right? So in other words, it has that 1 bit that I sent in some position and 0 everywhere else. Okay? Now, this is where we get into the discussion about what you had asked about with the precursor. So you should notice here that I didn't necessarily place this at the 0 position. Okay? I could basically say that I want my desired thing to show up 2 symbols later, or 10 symbols later, or 5 symbols later. Okay, so what you have to be careful with there is that has to deal with 2 things. It has to deal with just what's the delay of the channel itself, A, and B, what's the delay that you're quote-unquote inserting in your equalizer because you have precursors. Okay? So just, again, be careful with that because it's a source of sort of great confusion. If you don't place the desired thing in the right spot, your equalizer won't be doing exactly what you thought it was. Okay? So notice this desired thing, you have to sort of insert the zeros in the right spot to actually get it to behave the right way. Okay? So what I'm really sort of saying by this, again, to just sort of go back to my specific example, what I'm basically saying is that my Z desired, just as an example, would be like this. Okay? Here I didn't allow any delay in the channel, but that's okay. The channel, in my particular case, didn't have any delay. Okay, and so notice I used actually 5 entries here. That was just the same dimension that I had in my channel matrix. Okay? My convolution matrix there. Okay, so now we sort of get to really the meat of it. So using kind of the things that I formulated already, what is it that I kind of ideally want to be true? What's kind of the equation that I want to be true? What do I want to be equal to what? Anybody have any thoughts?
Cascade.
Heard somebody say something.
YTX multiplied by HCH should be ZTX or ZRX.
Okay, so
Or
basically,
Z.
so we know that sort of by definition ZRX is indeed equal to the channel convolved with YTX, right? But what we really ideally want is we want it so that that ideal desired received symbol, which I've called Z desired here, should be equal to, as you said, that channel basically applied to, and let me just write it this way, to YTX, which remember YTX is really just whatever my equalizer coefficients were, right? Because remember what I'm transmitting is just a single bit on the transmitter, right? So when a single bit goes to the transmitter, or a single 1, if you looked at the output, first it would be W0, then it would be W1, then it would be W2, right? Which again is just WZFE. Okay? So what we're basically saying is that ideally speaking, we want this desired single perfect bit to be equal to that channel matrix times the equalizer coefficients.
Why it's channel times coefficient, not coefficient times channel?
Because here I did transmit preemphasis instead of receive equalization. If I did receive equalization, then you have it the other way. By the way, the thing to remember with matrices and block diagrams, unfortunately with block diagrams, if the arrows are pointing to the right, then when you write the equations, you have to start at the right and work your way left. Okay, just that's unfortunately how things turn out, but it doesn't matter too much. Okay.
It's times the transmitted waveform, right?
Right. So I'm assuming here that the transmit waveform basically looks something like this, but it's just potentially shifted earlier in time. Okay. Does this make sense? Or? Okay. So now here's, let's say, the $1 million question. Am I done? Can I solve this equation?
You have 3 unknowns, but you have 5 equations.
Ah, there we go. So
So
maybe she was better than me when I first looked at these things. He basically said you actually have 3 unknowns, but 5 equations. Okay, so the way to see that is, remember that H channel there, it has 5 rows, right? And 3 columns. And similarly, that WZFE only has 3 rows, right? And what we're basically saying is that we want that to be equal to something with 5 rows. Okay, so if you kind of remember your basic matrices, what this is kind of saying is, you take the 3 entries here, you multiply it by the 3 there, that gives you one equation. Take the 3 on the next row down, multiply them that gives you another equation, and so on and so forth. So indeed, you have 5 equations and only 3 unknowns. Okay, so in general, tough luck. You can't actually directly make this to be true. Okay? So now maybe somebody who remembers linear algebra or one of these things. So since you can't do this, what do you do?
Least square.
Yeah, exactly. You do least squares, right? You just do some sort of least squares fit. Okay, so what I mean by that, for those of you guys who haven't seen this in a while, is, again, since you can't set equal, instead what you want to do is minimize the so-called mean squared error. Okay? So again, what I mean by that is essentially, what I want to do is pick my WZFE so that I minimize essentially the difference between what it was that I wanted and what I'm actually going to get. Okay? And when I say minimize the difference, what I mean is in the mean squared sense. All right, so each one of these entries, I basically take the difference and square it, and then I add it to all of the other entries doing the same thing. Okay? Does this make sense to everybody? Or? Okay, so now, just as, kind of a reminder, I'm not going to walk through the derivation. It's not that actually bad, but it's just essentially simple linear algebra. The result, if you do that actual optimization, which again is just coming from least squares fitting in linear algebra, is the following. The coefficients that you'd want to use are equal to the following slightly annoying and complicated, but not too bad. And there's a transpose there. Inverse times. Okay, so that's it. Okay, so again, looks slightly complicated, but all this thing is saying is this H transpose, and by the way, transpose just means you flip all the rows and columns. Okay? So you take this matrix, which is H transpose times H, you invert it, you multiply it by H, and then I missed the transpose there. You multiply it by H transpose, and then you multiply that by your desired signal. Okay? So now, by the way, just in case you don't believe me, and maybe you should do this as a homework exercise, the dimensions do indeed work out. Okay, so this thing here is a 3 by 3 matrix. Okay, that there, if I include the transpose, of course, is a 3 by 5 matrix. This is a 1 by 3, actually 3 by 1 vector. Okay.
Is that 5 by 1?
No.
Oh, I'm sorry. Good. You guys are paying attention. 5 by 1 vector. Okay. And then this, of course, is a 3 by 1 vector.
Question.
Yeah.
So the one in the middle there is always invertible?
So yes, it is always invertible, because notice when I do H transpose times H, by definition that's invertible. Okay? Because essentially, anyway, it's linear algebra. Again, if you want, we can go through in more detail, but that is by definition always invertible. Okay? Yeah.
How do you choose the number of taps in their file?
That's up to you. So I've said nothing about what that is. You have to arbitrarily choose it right now.
So you're just saying if it's long enough, you actually can solve the equations.
Okay. Well, so it depends on what exactly the channel looks like, right? So, but you are right that there are cases where you can directly solve for it, right? So there are channels with some number of coefficients where you could just directly solve what are the coefficients that perfectly invert that channel. Now, if you'll sort of notice, and I'll just go back to this picture right here. If you'll notice, there's a lot of these little suckers, right?
Sure.
So yeah, you could maybe build a 20 or 40 tap, and okay, that is actually potentially possible, but generally speaking, people don't do that. Only because, it costs you power, costs you complexity, and so on and so forth. And then, of course, the question is, how much does that really buy you at the end of the day from a performance standpoint? I think there was 2 more questions. Okay, same thing. Same thing. Okay. So, by the way, just since you asked, although I was going to do it anyways, I'll give you a homework problem. Will you indeed solve it exactly?
Actually, I have a question about the number of tabs. The more tabs you have, it's kind of like you're going to translate into latency, right?
Mm-hmm.
Is there any case you actually care about this latency?
That's a great question. So indeed, there are many cases where you really do care about the latency. So specifically, if you're talking about something like, a microprocessor talking to another processor, or a processor talking to a graphics card or something like that, you do care a lot about the latency. Right? And so from that standpoint, if you end up inserting a lot of latency because of, some equalizer or something you're doing, that could actually be a big deal. Okay, in fact, for those of you guys who are, again, familiar with the wireless kind of stuff, a lot of times not the only, but one of the main reasons people don't do coding is because of the latency. So even if it was really good and, it didn't cost you any power, they wouldn't want to do it simply because it would insert extra latency. Okay, so that is actually a very good question. Yeah?
So in practice, we don't know the channel.
I'll talk a whole, you're going to get an entire lecture about how you figure out what the channel is.
Okay,
So if that's your question, don't worry, you'll find out.
Okay.
But, briefly, you can essentially do some least mean squares algorithms also to estimate what the channel is.
Does it have to be iterative, or?
It does not have to be iterative. There are ways you can make it non-iterative. Usually you need to know what the data pattern is to sort of do that. But most of them are indeed sort of iterative types of algorithms. Or rather, they look a lot like feedback loops, so to speak. And again, we'll see exactly what those are in a couple of weeks.
A small question, but for the desired, maybe the third element should be 1, right, in this case?
Oh, it depends. So in this particular example that I came up with, I made it so that I wanted a symbol delay of 0, and so I left it at that first one. But if I wanted to change what the sort of number of precursors versus number of postcursors, I could have flipped it around.
Yeah, but when you're defining this H channel, actually you zero-pad it for the first, second row and fifth, fourth rows.
Yeah, but so notice the first thing that's going to come out is H0, right? And if H0 is my main bit, then the channel delay is 0. Right? So if I put a 1 right here, then the very first thing that will come out will be H0.
Okay.
I guess
right?
for equalizing on the transmitter, then time is relative to the transmitter.
Okay, well, so that's right. So you have to be careful about, so in this thing, if I put like a 0 right here, you still would have needed to shift your z desired, right? Because the z desired is coming out on this side. Right, so if the channel itself had delay in it, then you'd have one symbol of delay in that z desired over here just from the channel. Does that make sense? Or?
I think it'll fall out when we talk about how to measure the channel.
Okay. Your question may also fall out when you actually do this on a homework once and you see what works and what doesn't. So if that doesn't answer it, then we'll certainly talk about it more later when you estimate. But okay, well actually, so maybe I understand your question. If you're talking about estimating sort of like what the coefficient values are, then indeed once you're sort of either getting to the receiver or sending information back to the transmitter, then the way you typically do that is indeed relative, right? So if you sort of know where your cursor is, or you just assume that you are at the right spot, then you indeed figure everything out relative to that cursor, right? So you'd say, okay, the precursor needs to be this, and the postcursor needs to be that, and so on and so forth. Is there a question in the back, or? Okay, great. So now that we got through most of the math, then we can actually now sort of come back and take another sort of intuitive look at this. Okay? So the first thing I should mention is that if you just went, you plug this into MATLAB, which again you will do, in general you can't actually take that result sort of directly. Okay? And the reason for that is the following. What this will really do is it'll literally take whatever loss there was in the channel and try and compensate for it. Right? So in other words, if you had like 20 dB of loss, this thing will try and put 20 dB of effectively gain so that you still get, if you had a 1 volt at the input, that you have 1 volt at the output. Okay? Well, as you can probably imagine, there's actually a maximum signal swing that you'd like to put out of your transmitter, right? So that means that what you have to do is you have to make sure that the maximum signal you transmit, including all of the equalization stuff, is still fixed. And then what you can only do is sort of scale things underneath that, right? So in particular, what that usually means is that if you looked at sort of what happened with this black, that was my transmitted pre-emphasized waveform. If you compare the magnitude of this green pulse to that red pulse, which was the unequalized thing, notice after equalization, the amplitude I get is smaller, right? Because basically if I kept the peaks the same as I used to have, then in order to do that equalization, my only choice is to make things smaller, right? To say it another way, I'm kind of, in order to emphasize the high frequency stuff, I have to de-emphasize the low frequency stuff. Okay, and by the way, sometimes when you put it on the transmitter, people will call it either pre-emphasis or pre-de-emphasis or something like that. Okay? Does that make sense to people? Or okay, so as we said, if I keep the same peak signal swing, then my received amplitude is smaller. Now here's the question. Is that a problem? Is that a big deal, or who cares?
Depends on how much your amplitude got decreased by. Right?
Okay, yeah, so you're saying it depends on how much your amplitude got decreased by. So let's say it got decreased by, I don't know, 40 dB, 20 dB. What would be the issue? What would start hurting? Yeah, your SNR, basically your noise, right? So the real fundamental issue, which we hinted at a little bit earlier, is just that if you actually look at what your transmitter is doing, your transmit FIR filter, if this was my unequalized response, and I wanted to flatten this thing out all the way to 2.5 gigahertz, kind of my only choice is just to knock everything down to the worst case loss, right? So that means that I'm literally just throwing away a bunch of signal, okay? If I take a smaller signal and I feed it into my receiver, then of course that smaller signal relative to the noise will have worse SNR, right? So this is actually fundamental to doing equalization, at least with doing linear equalization. Okay, and so it's so fundamental that people sort of have a term for it. It's called noise enhancement. Okay, so anytime you do equalization, you're always going to be enhancing the noise relative to your signal. At least, sorry, anytime you do linear equalization. Okay?
More so on the transmitter, right?
Okay, so I was hoping somebody would ask that. Turns out it's totally equivalent. Doesn't matter which side you do it on, you're going to have that problem. And the way to think about that is just the following. Right? So let's say that I put the equalizer on the receiver. Right? Well, guess what? This will be now my WZFE. Right? That's my receiver. That's my comparator. But remember, that thing had gain. So you're applying gain to the noise. Right? So in the transmitter, you're applying attenuation to the signal. On the receiver, you're applying gain to the noise. But it's completely equivalent.
Are we making some assumptions about where the noise is coming from? Or?
Okay, so good. So you guys are circuits guides, so that's good. So usually when you talk to the comm people, they just sort of assume this is, the fundamental thermal noise that's out there in the world of you transmitting a wireless signal. Okay, which, by the way, even here exists, because you've got a 50 ohm term at the end of your line, right? And that has some fundamental noise in it. So you're absolutely right that when you really build this, that's going to have its own noise contribution. And if that noise completely swamps all of this junk out, then, then it's kind of a different issue, right? But this is indeed sort of something to keep track of because, if you really optimize the link, then pretty quickly you'll start hitting cases where either this noise matters or even in fact what's inside of the ZFE will matter. And even from that standpoint, when you do the equalization internally, that also has some penalty from a noise standpoint. Okay, so that's actually a great question. When you talk to the comm guys, they're really focusing on sort of, that KT noise floor. Okay, that's really what they're mostly focusing on. But this same idea actually also applies to even if you build it with a real circuit. And by the way, even if you're not talking about real fundamental noise. Sometimes people will tell you that something like this looks bad simply because essentially you'd be amplifying things like crosstalk more, right? Because you're sort of doing a high-pass filter, and the crosstalk might be high frequency, so you might be amplifying that. Other questions? Or okay, so kind of the key point here is that, again, you are going to be doing this noise enhancement, and as you can maybe guess from kind of the picture here, this is a particularly big issue in a channel that has a big notch in it, right? Because if you've got a big notch, then when you do the equalizer, your only choice is to knock your signal down all the way to the bottom of that notch there, okay? At least if you really wanted to fully compensate for it. Okay, so that's pretty bad news. So the quote-unquote good news is there is kind of another way you can do linear equalization that doesn't quite have as bad of a penalty from a noise standpoint. Okay, so what this is called is MMSE, okay, or it stands for minimum mean squared either error or equalizer. Okay, so the idea here conceptually is actually very simple. It's just saying, look, before all we did was we said we wanted to take this thing that looked like that and force it to be 0 everywhere else. Well, nobody said that that's the best solution, right? Nobody said that you should just completely ignore the noise and force all the ISI to be 0. So what this new equalizer, or this MMSE, is essentially doing is it's just going to say, why don't you find the right balance between the noise and the ISI? Okay, so in other words, why don't you minimize the overall mean squared error, including the fact that there's actually noise in the channel? Okay? Oh, so just so that you guys sort of have it, I'm not going to derive this because it's a little bit annoying, but it's actually not, you can do it. It's not too bad. If you wanted the MMSE equalizer, then instead what you will get is something that looks like the following. So actually, it turns out the only place I'm going to make a modification is inside of that matrix that we're going to invert. And I'm just not going to write the full thing. I'm just going to call it H now, because again, I'm lazy. Okay, so that's actually how you do the MMSE equalizer. So notice the only thing that I added versus the previous formulation is just this term right here. And for those of you guys who don't remember, this I here, that's just the identity matrix. So it just has 1s on the diagonal and 0s everywhere else. Okay? Yeah?
What's the unit you use for SNR?
Ah, okay, so this is in voltage, or voltage squared to be more precise. So in other words, this is like the sigma squared of the signal divided by, well, SNR is the sigma squared of the signal divided by the sigma squared of the noise. Okay? So what you can kind of see here is that you remember before we didn't actually have this term at all. This is kind of telling you that if your SNR is small, then forget about what the channel is. You're only going to do your gain based on just what the noise is. Okay? Yeah.
There's a transpose out there, right?
Yes, that's right. There should be a transpose right here. Thank you. Okay? So again, that's the only difference. It's just that rather than directly sort of inverting the channel matrix, you just add in this SNR term right here. Okay? So just to kind of give you an idea of how this works out, what the MMSE is really doing is saying, I'm going to allow some residual ISI to stick around in my response. But the idea is that if I do that, then I'm going to be amplifying the noise less. Right? So essentially, if you kind of look at it, this black trace here, if that was my original unequalized response, which is just some bogus thing that I made up, then if this red thing here, that was my ZFE solution. Okay, and I think I did this with two taps. Okay, so what you can see is basically that ZFE, it really zeroed out the ISI, right? Well, if I make the SNR sort of not super high, and I now do an MMSE, what you can see with this blue response here is that, there's a little bit of residual ISI right there that I kind of allowed. And in fact, maybe even a little bit still left right there too. And it turned out that for this particular channel and the particular SNR I chose, on a net sort of mean squared error, it was better to leave that ISI than it was to amplify the noise and try and kill that. Okay? Does this kind of make sense to everybody? Or? Okay, so there's unfortunately, let's say, some not so good news about this, which is, despite MMSE being very interesting, if you go and you talk to the comms people, or if you do any kind of wireless stuff, they'll say, oh yeah, I have an MMSE equalizer. It's very, very rarely used in links. Okay, and the reason for that is kind of, there's two sort of straightforward reasons. The first is that it's a little bit trickier to figure out how you actually adapt this equalizer, which again, we'll talk about more later on. But the other thing is that oftentimes you may not really know what the noise actually is. Okay, because usually you've built the link to kind of make the noise really small in the first place. Because remember, you're shooting for like 10 to the minus 15 bit error rate or something like that. So actually really measuring what the noise is down in that error rate is pretty darn hard. Okay, so again, not that this is impossible, but typically not used, anywhere near as often as sort of these zero forcing solutions. Okay? Yeah.
So if you do indeed estimate the burr, then is it equivalent to doing an MMSE or is it not exactly?
Well, okay, so you could do what's called a minimum burr equalizer, and there are some people that have done some work on that. The biggest issue with most of them is that, if you really want to do that, let's say the quote-unquote right way, or you really minimize the burr, it takes a freaking long time to measure 10 to the minus 20 or 10 to the minus 15 for each and every single point.
Yeah, sure. I'm just asking if you do indeed go down that path and even if it takes long.
Oh, will that actually be MMSE?
Is it exactly
okay,
the same?
So no, not exactly. So it turns out if you actually did something that was purely minimizing the burr, that would not necessarily be exactly the MMSE solution. The reason for that we'll actually talk about next lecture. It just has to do with the fact that when you sort of write things this way, what you're intrinsically assuming is that kind of the residual ISI looks kind of Gaussian, meaning its distribution looks kind of like the distribution of the noise. But if the residual ISI does not look Gaussian or has some very different statistics, then this is not the Burr optimal way of handling it. Okay? Like I said, we'll actually talk some more about that probably next lecture. But from 20,000 feet, that's kind of the reason why there's a distinction there. Other questions on this? Or? Okay. Oops. So, I talked about MMSE. I said that, that's nice, but unfortunately we can't really use it all that much. There is, however, a piece of good news, which is there's another way of getting around this noise enhancement problem that is actually used and is actually very applicable. Okay? So the key kind of insight to getting to that, this final type of equalizer we're going to talk about, is just to realize that, if I look at my pulse response here, right? Let's say that I really got something like this. And let's say that somehow or another, I actually detected this bit correctly. Okay, so somehow I figured out that this was supposed to be a 1, right? Well, if I knew that this was supposed to be a 1, then I actually know what all of the future intersymbol interference will be, right? As long as I know what the channel is, right? So if I know what that will be, why don't I just go ahead and, based on me knowing that this was a 1, just directly subtract out all of that residual response. Okay? Does this kind of make sense to people, or? Okay, so, this may sound sort of crazy because it's obviously a recursive loop because you have to make the right decision the first time in order to cancel everything afterwards. But this is exactly what people actually do. So this is what's known as a decision feedback equalizer, or DFE. And so, if I slur my words or whatever and I say either D or Z, hopefully it'll be clear based on the context as to what it is that I'm actually referring to. So DFE, again, is decision feedback equalizer. So the idea here is very simple. So what you basically do is you say, okay, I'm going to make a decision just on whether the bit was a 1 or a 0. Once I know if it was a 1 or a 0, then basically all I have to do is take that 1 or 0, pass it through some FIR filter, which just creates the reverse, or rather the negative of the channel, and then take all of that stuff and subtract it off from my incoming data, right? So in other words, as long as I made the right decision over here, and I got sort of a perfect digital bit coming out, then I can just literally subtract all of this residual stuff afterwards. Okay? Yeah?
My question with this thing was, it depends on the first bit, right? If you got it right, yes, you got the other thing right. But what happened if you actually got it wrong?
Okay. So we're going to talk about that more in 1 second. Okay? So that is indeed one of the issues with this type of structure. But we'll talk about that more in 1 second. Okay? So again, just to make sure sort of this is clear, the reason why this is advantageous is by doing this, you're not enhancing the noise at all. You're not multiplying the noise. Okay? And the reason for that is that once you have a digital bit, that digital bit is just a digital bit. It's a 1 or a 0, right? So in other words, it has no information about what the noise beforehand was, right? So then when I take that digital bit and I use it to just feed back and subtract all this stuff off, notice the noise itself is never coming back into this filter here, right? If the noise was sitting like, being added right there, once I've made the decision and I've made the right decision, that noise has no way of making it back through that filter. Okay, in other words, it has no way of me amplifying the noise. Does that kind of make sense to people, or? Okay, so now we're going to get to some of the questions that were asked. Oh, that's interesting. Okay, so the first is that, you know, as you can maybe tell by this, if I'm going to build a DFE like this, you can only subtract, you can only cancel things that happened after you know what the bit is, right? So in other words, you can only cancel post-cursor ISI. Because if you have a precursor, you haven't actually decided what the bit was yet. So you have no way of subtracting that out. Okay? So that's the first thing. So because of that, by the way, a lot of times you'll still need to combine that decision feedback equalizer with some linear or FIR or what's called often a feed-forward filter in front of it, so that the feed-forward filter can take care of any precursors that you might have, and that the DFE will take care of all of the post-cursor stuff. Okay? The other thing, which is of course what Charles was asking about, was, well, okay, this all sounds great, but what happens when you make a mistake? So you guys tell me, what happens when you make a mistake? Or what could potentially happen when you make a mistake?
Basically make the ISI worse because you're adding opposites.
Yeah, exactly, right? So if you ever make a mistake, what you're basically going to do is double the ISI, right, on that particular bit that you got wrong, right? So the question then becomes, how bad is that? If the ISI was so bad that by you getting that wrong, you're guaranteed to make another wrong decision, then unfortunately you're hosed. What's going to happen is you're going to keep making wrong decisions over and over and over again, right? So that's what's called error propagation, right? Because you have a feedback loop, and once, if you seed it badly enough that it gets stuck, then you're just stuck, okay? Turns out in high-speed links, this is not too big of an issue, because remember we said we were shooting for something like 10 to the minus 15 error rates, right? So it basically means that, okay, yeah, if you once in a really long while make an error, the chance of you then, making an error that's so bad that you're then completely hosed is usually still small enough that it's not a big issue. But that's not to say it's something you can ignore. So error propagation is certainly an issue, and if you look at some of the really bad wireless channels, that's why people tend not to use DFEs in those instances. But for most high-speed links, this actually works out pretty reasonably well. Like, I haven't seen anybody come back and say, oh, damn it, my DFE just got into this error propagation thing, and I had horrible issues and things like that. Does that answer your question, Charles? Or? Okay, great.
So this is all on the receiver, right?
This is now totally on the receiver, and it has to be on the receiver because you need to know what was the received bit.
And if we're not see, then these need to be sort of analog.
Yep. So
stuff, right?
That's maybe leading to what I'm about to say here, which is, remember we said we want to run these things at, let's say, I don't know, 10 gigabits per second to, let's say, 20 gigabits per second? Well, if you want to do that, and you want to build a structure that looks like this, then that basically means that you have to do all of the following in at most 1 bit time. Okay, and by the way, UI just stands for unit interval. That means 1 bit time. I'm just using that here because it's shorter to write. Okay? So you have to do all the following things in 1 bit time. You have to decide what the bit was in the first place, which remember usually involves regenerating a small signal, right? You have to feed that back through some multiplier, meaning you have to scale the bit by some coefficient. Then you have to get that onto some analog node and settle that analog thing out, all before you make it back to the comparator. Okay? So again, as an example, if you're going to do this at 20 gigabits per second, you have less than 50 picoseconds to do all 3 of those things. Okay? Now, by the way, people usually really focus on that first tap, because that is indeed the hardest one. But you have a similar constraint everywhere else, right? Because off of this flop, you of course have to get out, settle the analog node. Off of here, again, get out, settle the analog node, and so on and so forth. Okay, but indeed, that very first tap there is usually the toughest one to actually make happen. Okay, and actually for a really long time, people sort of avoided doing this simply because they couldn't figure out how to really close that loop there. Okay, so we'll actually talk about, let's say, a lot of the more recent advancements that people have made. This is now actually a fairly common technique. There's a lot of tricks you can apply to, in fact, even get it to work up at these 20 plus gigabit per second kind of data rates. Okay, even actually in sort of a current technology. Yeah?
Can you skip one of the taps and just take care of that in the linear equalizer? Just
Okay,
like it
so
is in
there's
Beaker?
actually lots of combinations that people have come up with. So indeed, what some of the people did initially was they said, well, darn it, I can't close this loop. So instead, what I'll do is I'll just skip that tap and somehow try and deal with it some other way. It turns out that particularly in high-speed links, that didn't work out so well for the following reason. And actually, I guess this one shows it too. So if you've got a dispersive channel, turns out you tend to have a lot of junk right next to you. Right? And in particular, that first post cursor tends to be pretty darn big. So a lot of times, if you did that, you kind of lost a lot of the advantage of doing the DFE in the first place. So if you looked maybe about 5 to 7 years ago, you would see a lot of these solutions that kind of had so-called gaps in the equalizer space, where the DFE just couldn't actually cover it. These days, almost all of them, if they have a DFE, they're covering the things close by you, and then maybe they're covering things later on. Okay, so there's actually sort of optimizations that people tend to do in the other way, which is they may do something like use the DFE to cancel only that one tap afterwards, and then let the linear equalizer take care of everything else after it. Okay, and the advantage of doing that is just now your linear equalizer kind of is dealing with lower bandwidth signals. So that's a great question. Yeah.
So to do DFE, basically we don't want the noise amplification, right? But
Right. So the fundamental difference between DFE and a linear equalizer is only that you don't have noise amplification.
But what I mean is, if you have this feedback, you basically have ended noise and the input at the same time.
You're just saying that, hey,
Yeah.
fundamentally these are devices, and those devices
Yeah.
have noise. So yes, that's right.
But how does? I think it's maybe a square root relationship depending on the number of.
Well, no. So,
I mean,
so as I said, and I am guilty of this. For this lecture, I'm mostly focusing on sort of the communication side of it. You're absolutely right that from the standpoint of how you build the circuits, it's not immediately obvious that the noise you've added from this transistor is all that much better than the noise that would have come from something else, at the very front end. Okay, so again, this actually has a lot to do with you have to look carefully at where is the noise in your system really coming from. But you can imagine that if indeed I have some, linear equalizer or something with gain in front of you, then if you've done kind of a good job with the chain, usually your noise will be dominated by the front end stages and not by this later stage here. It's not universally true, but generally speaking, that's the case.
So I was thinking about maybe there's a limit on the number of taps you can use, such that it's still beneficial over.
Okay. So you were saying that maybe there's a limit on the number of taps we can actually use. We'll talk actually a lot more about that when we talk about how we really build these. But indeed, there's some implementation issues related to how you'd actually build this. So I think we're actually out of time for today, so we'll finish this up next week, and then we'll move on from that point. So see you guys then.